Hello, I'm Stu Schultz, and this is the video version of the AAPT workshop called Electrostatics, or teaching about electrostatics. You have the videotapes, obviously, because you're seeing me live right now, but you should also have the manual that is available from AAPT. It's highly recommended that you have this in accompanying the workshop because a number of the activities that we do, well, in fact, all the activities we do will be in the manual, but the manual also has in it additional activities and references that you may want to use. So right there you can see the address and phone number of the AAPT, and what you want to ask for is the manual called Teaching About Electrostatics by Robert A. Morse. This is an excellent manual and has, again, let me say, a lot more additional information than what I'll be talking about just in this videotape. The videotape that you're about to watch is broken down into 3 one-hour segments. Each one of those one-hour segments, in turn, is broken into 3 20-minute topics that we'll be dealing with. Each one of the topics will be carried out in a similar format. That is, we will first of all talk about some of the theories, some of the ideas, some of the concepts that are going to be involved with this. We'll then show you the materials that you will need to carry out the activities and then invite you to stop the videotape and do these yourself. This is not designed to be a passive tape. I mean, I couldn't imagine anything worse than to sit and watch me for 3 hours straight without a break. So we're going to want you to stop the tape, carry out these activities yourself, and then after you've given this a try, turn the tape back on again, and then you will see the participants of our live workshop actually carrying out the same activities you have done. At that point, you might have some other ideas or additional ideas of things you want to try with the materials that you have available, and at that time, of course, it would be appropriate to stop the tape again and try those for yourself. Let me just go over for you the titles that you can expect to be covering in this workshop. During the first hour of videotape, the 3 20-minute segments will be as follows. There will be the separation of charges, charged tapes, electroscopes, and that will consist of the first hour of the program. The second hour will include the topic electric force, electric dipole, and using neon bulbs in electrostatics. The last hour will include making and using Leyden jars, making an electrostatic generator, and finally making an electrostatic motor. So, I hope that you enjoy this video. I hope that it is useful to you, and I hope it teaches you some of the concepts about static electricity, and most important of all, that the ideas that are presented here you will be able to transfer to your classroom. Now let me tell you that the activities we're doing are designed to develop the concept of electrostatics for yourself. You as a professional educator will have to decide which one of the activities you choose to use in your own classroom and what is going to be appropriate for the grade level that you teach. We're actually, when you see the participants in our workshop, they will be teachers from K through 12. We have all grade levels represented and a total variety of backgrounds. Some have actually had no formalized training in electrostatics whatsoever. Others have had a number of different physics courses, and so they have more experience. Our plan is that the videotape will provide the media by which you can review this over and over and over again. If you have an excellent background in electrostatics, you might just pick up a few ideas and never have to review the tape again. On the other hand, if this is all new to you, you may want to watch a tape over a number of times until you're comfortable with the activities. We know that you are not going to use these in your classroom until you're actually comfortable with the concept. And so our goal in this tape is to make you comfortable enough with the concepts to use these ideas in your classroom with your youngsters. Well, I hope you enjoy this. Okay, this is the first segment of our workshop, and this is called Separation of Charges. Before we get into the real fun of electrostatics, I want to go over a few of the fundamental concepts with you so you can understand what's going on here. First of all, you need to understand that all matter is made out of charged particles. These are atoms. Sometimes the atoms are combined in the form of molecules. There's various structures of material, but there's one fundamental common thing that's true of all matter, and that is that there are charged particles in the material. So, here we have a sample, just a general type of material right here. You have these positive charges right here that are the larger circles, and the smaller circles that represent the electrons or negative charges. Now, in reality, the positive charges reside in the nucleus of atoms, and they tend to be very, very small. So in that sense, this model is not accurate. But anyway, we have positive charges. The important thing to know is that these positive charges are locked into the structure. That is, they don't move off or on the material. The electrons kind of float around in various structures, and some structures are held quite rigidly in place. Other structures, they are like flowing around fairly easily, and as a matter of fact, sometimes described as a community sharing of electrons, meaning that all these positive charges would be represent atoms, and these atoms would be sharing their electrons in a communal kind of a fashion, meaning that the electrons could move very freely through the material. That type of material would be a conductor. Now, a sample of that would be like a metal bolt or, of course, an electric wire. That's the purpose of the wires, to be a conductor. So these conductors have electrons that can move through them very, very freely. There are other materials that are non-conductors in which the electrons can't move with ease from side to side, but it turns out that it is possible in many of these to take the charges and separate the charges by rubbing off the electrons. In every case, though, if you take a material like this, it's only the electrons that can be taken off or put on. In some cases, the electrons can be added to the material. In other cases, the electron can be taken off. But that is what amounts to charging an object, is by separating these charges. But remember that the charges, when we're separating them, we're going to be moving electrons only. We can't move the positive charges. Now, the other thing, the idea that's important is the forces that are between these charges, because the way we're going to tell an object is charged is by our own observation of some force, something moving, something causing it to move. And so here is an equation. This will be the only equation we'll have to deal with, but it describes a force. Now, this is an equation referred to as Coulombs' law, but as you can see, there's a couple of important ideas right here. The force right here is equal to a constant K, and then the amount of charge in the first object and the amount of charge in the second object. Now, think for a minute. If you had one object that was charged and another object that was not charged, there would be no force. So you have to have two charges, and then the distance apart is the value r right here. This is what's called an inverse squared term. All that means is if you have two charges that are some distance apart, if there's a certain force on those charges, if you double the distance that they're apart, the force will only be 1/4. So what it means is the force decreases very, very quickly as you separate these charges. And you'll see this when we begin carrying out the activities. Probably most important about this that you remember is the fact that the charges can be positive or negative. This was assigned by our famous American Benjamin Franklin. And this was kind of picked arbitrarily, but we'll be talking in this workshop about ways you can determine whether it's a positive or negative charge. For right now, the only thing that's going to be important to us is are the charges the same or are they opposite? In other words, if both the charges are positive or if both the charges are negative, you will see a repulsive force. On the other hand, if one is positive and the other is negative, they will then attract each other. So you can summarize this with this statement: like charges repel and unlike charges attract. That's really all you have to remember. Like charges repel and unlike charges attract. Now, that will be once we get the charges separated, but how do we go about separating the charges? Well, in every case, we'll be carrying out a simple activity simply by rubbing these objects together. In other words, here we have a little graphic model of what you might consider a piece of cloth. The orange would be a piece of cloth, and the green could be like a piece of styrofoam right here. And as I rub this back and forth on the material, we transfer electrons. Now, the electrons can go either way. In this case, let's say the electrons go from here onto our styrofoam board. Now, notice what has happened. Before I rubbed this and the electrons are transferred, we had equal numbers of positive and negative charges in each one of these devices. Let me go back to that and show you what that looks like. If I put these little electrons back up here again, you'll notice that for every positive charge, we have a negative charge. Again, this is simply a model. It's not a very accurate model because our positive charges reside in the nucleus. The electrons are on the outside. And there would be many, many more. There would be millions and millions and millions of these charged pairs right here. And we only really are rubbing off a very small number of the total number of charges. But up here on the orange, we have an equal number of positive and negative charges. If you care to count those up, I think you'll see that the total number is constant. There is a little negative charge right down here, so don't forget that one. The same thing is true down here. Just trust me, you don't need to count all these up, but as you can see, positive, negative, positive, negative, positive, negative, all the charges are balanced. So this would be an uncharged object, and this would be an uncharged object. Once you rub these together and the electrons are transferred from one object to the other, we now have an excessive number of negative charges on this object and a deficiency of negative charges on this object. This object, therefore, would become overall positively charged. Whoop. That's not right. This is going to be overall negative charge because we have the excess electrons on there, and this object would become overall positive charge. And we accomplish this simply by rubbing these two dissimilar materials together. It turns out that in your manuals there's a page that shows you the electronegativity chart, and you can see the great variety of materials that are listed there, and they show which objects tend to take the electrons and which objects tend to donate the electrons, okay? And this is on the first page of section 3 of your manual, okay? This is section 3 of the manual, and right down here we have a list of objects showing which ones tend to be more positive. What that means is if these are positive, they give off electrons, and you can see at the top of the list is rabbit's fur. That is the most positive material, meaning that if you rub it with some of these ones that are below there, the electrons will go from the rabbit's fur onto the other objects. So the lower object would become negatively charged and the upper object would become positively charged. And what we're going to do in this segment is simply experiment with different combinations of these materials. So if you step over here with me right now, I'll show you the materials you want to assemble to try out some of these activities. Over here on our lab table, we have gathered together a great variety of materials. And let me just go through some of them with you. First of all, this is the largest one. I can use this as a pointer. This is our golf tube. This is an insert plastic tube for golf to put in the golf bags. We have these plastic, kind of hard plastic plates. These are the styrofoam plastic plates. Here we have the hard plastic cup, one version of a coffee cup, another coffee cup. Over here we have different samples of cloth material. Here we have here's our rabbit's fur right here. Over here we have objects such as, this is some paper from a straw holder. You can get those at your friendly McDonald's stores. More straws. Here we have some rulers, plastic rulers, plastic marker. We have another wooden ruler, some various types of plastic bags. This is an overhead transparency sheet, and finally we have here some of this blue board insulating material that is used on homes. Essentially, any two of these rubbed together may or may not create some electric charge, but how are we going to see if there's an electric charge? Well, here's what I'd like you to do. Assemble material similar to this together. You don't need to have every single one of these. All you need to do is have a few of these and a few bits of paper. So I'm going to use this straw envelope here and just cut up some really, really fine bits of paper right here. And this is what we're going to use to determine whether or not we have that electrostatic force. And then basically you can choose almost any two objects you want. Here there's this little plastic straw. And here is my rabbit's fur, and I'll simply rub these together now and see if we get any kind of electrostatic charge from this. The way we can tell is there an attraction? And you can see right here we had some attraction and some repulsion, so you did see the electrostatic force. Then you simply try objects. Try the coffee cup and the fur. Or you may want to try the coffee cup and the wool. Whatever combination you want to try, we want to encourage you to do it. Try 3 or 4 different combinations and see what happens. This is for you to experiment with and for you to experience. So we'd like you now to stop the tape, try your materials, see what combinations happen, play with this for a while, and then when we come back, we'll show you what our participants did in a workshop that we held after this meeting. Okay, finally it's your turn. Now, what the participants are going to be doing when you watch the tape is to turn this off at this time and then they'll come back and watch what you do. Basically, all through this workshop, we're going to be asking you to experiment, okay? So it's up to you to create your own ideas. The fundamental idea here is that matter is composed of positive and negative charges. The positive charges are not mobile, but the negative charges are. Those are the electrons. Electrons can be either rubbed off or rubbed on, depending upon the nature of the material. The chart on the first page of section 3 gives you a listing just by experimentation which is has the greatest affinity for electrons. So for example, rabbit's fur does not hold on to electrons very well. So if you rub something with rabbit's fur, such as at the bottom of the list, let's say the hard rubber, that will take the electrons from the rabbit's fur and make the rabbit's fur positive and make the hard rubber negative. Okay? Was that clear on the tape there? Any questions about that? Yes?
What happens if you pick two things that are very positive, like rabbit's fur and glass?
Yeah, that'd be a good thing to try. Basically, I would think that you would not get as great as an effect. Okay? Another thing that you need to realize is that when you do electrostatic experiments with your students, the weather has a great deal to do with it. It's when the outside can have a tremendous effect. If this was in the springtime, it was a rainy, wet day, it doesn't work, okay? It's good to do this in the wintertime. Today is a cold winter day, and the humidity, I think, is down pretty low. And the reason for that is that the water molecule is like, you know, Mickey Mouse. If you picture Mickey Mouse with the mouse ears, okay? And one side is positive and the other side is negative. So if you create an object that has an electrostatic charge, let's say it's positive, the water molecules in the air in high humidity will turn the negative side around to it and just cancel that charge right out. And so water in the air will totally destroy electrostatic phenomena, okay? I'm going to show you a device later on that the electrophorus will usually work even though the conditions are bad, but that'll be for later on. Okay, we want you to try stuff today. Try things far apart on the list, try things close together, and let's just see what happens. If you have any questions while we're doing this, just don't hesitate to ask. And if something neat happens, let me know.
Complete equipment. But here's our
I think one thing that's important is in your mind as you try these different things out, be thinking conceptually about what you are doing when you rub things together. When you rub things together, you're either rubbing electrons on or electrons off, okay? And, you know, if you think about it, if you rub electrons off, they have to go on to something else, right?
right?
A lot of the electrostatic activities, as you can see, if you look around the room right now, lend themselves to experimentation. It takes very inexpensive materials, and students can be as creative as they can be in terms of trying to develop the electrostatic charges.
Something in the blue.
It
could be the blue. That would be a. Yeah, but that's actually what you would. It could be the maybe the paper on it. Like that.
You having fun yet?
Yeah.
Oh yeah. Now listen to me. Isn't it a lot more fun what you're doing right now than what you just did for the previous 20 minutes?
Yeah.
What'd you do for the previous 20 minutes? You listened to me talk, right? Now I want you to think about that when you're teaching your own students in your classroom. You know, when are they going to have fun? When are they going to be learning? It's going to be when they are doing, not just listening to you talk.
Okay, we're going through a whole list of stuff. Yeah, it worked. It worked out okay.
Okay.
Yeah, it took out a couple of three.
Got done with the paper on it.
Not like making your hair stand up. Check it out.
Now, you've all had a lot of fun, but I've seen almost entirely one kind of force, and that's been the attractive force. You know, you can also create a repulsive force if you get similarly charged objects. Yes. So now why don't you all try to get some repulsive forces going?
Wait, can we give two of these the same charge?
Pop off.
Let's see if they'll repel each other.
Yes.
We had repulsive or repulsion force between the spoon and the string.
But then it shifted, and then it was attracted.
When you shift?
Nothing. That's just it. At one point, we had it repulsing from one side of the string, but attracting the other side of the string.
End or side of the string?
Pardon me? Well, I say end, I should say. Yeah, not side.
Okay.
So when I have these two,
Oh, so one side attracts, the other side repels.
it
Okay.
did.
Now-
Now they're both attracting.
Okay, if you have a situation where there's an attraction, you know that the charges are opposite. If you have a situation where there's a repulsive force, you know they're the same. What happens on non-conductors, it's possible to charge them both ways. So you might have one side that's negative, one side that's positive on the same object. Sometimes, like on a large plate or something, you can actually charge portions of it one way and then rub another side of it with something else and charge it the opposite way. And you can get like negative and positive portions, yeah, like in a golf tube. You can make one end positive and one end negative if you rubbed it with two different materials. Another good question that's been asked is, why is it you can attract a neutral piece of paper with an object that's charged, such as we have here in this graphic? We have a positively charged rod right here. The piece of paper is represented by the oval shape. You'll notice that there are 5 negative and 5 positive charges. When I move in the positive charged rod, the electrons are able to move slightly through the non-conducting piece of paper to one side, and that will cause it to be attracted because opposite charges are attracted to one another. If I remove the rod, you'll notice that the force disappears and the charges redistribute themselves in the neutral piece of paper. Now, if this happened to be a conducting object instead of the non-conducting piece of paper, watch what happens now. When I bring in a positively charged rod, you'll see the electrons move more freely through the conductor and are displaced further to the side. If I then touch this object with my hand, it will allow additional electrons to flow on until they are distributed so that the object is essentially kind of neutralized. But now when I pull my hand away, those excess negative charges are trapped there. Pull the positive charge away, you'll notice that they redistribute themselves, but yet we have many more negative charges on there than we have positive charges. And so overall, we have charges by induction. We have charges negatively with a positively charged object. This is called charging by induction. Okay, well, I hope you enjoyed your experimentation trying a variety of objects and seeing how you could displace charge from one to the other. For this part of the activity, you're going to only need a coffee cup, some masking tape, and some thread. And what I'd like you to do is to just take the coffee cup, suspend, just put a little bit of tape on the bottom of the cup, put the thread up here. The thread is just suspended from some point. You can tie this from anything at all, just so you have this up in the air. And what we're going to do is to take a cloth, one of the cloth samples we had, and we're going to just rub this cup with the cloth to get this cup charged. And hopefully now there's electrons going one way or the other. We don't really know which way, but that's not the important point here. We simply want to have a charged object. Then I'm going to take another cup, same type of cup, and I'm going to rub that with the same cloth. And so I have two objects, hopefully, that I'll be charging the same way. What's going to happen when I bring these two objects close together? Well, this is where you come in. We'd like you to stop the tape now and try this yourself and see what happens. You want to tape the thread as close to the center as you can.
Give us a piece of thread.
Is wool on the list there? Oh, so wool's above styrofoam? Okay.
Polystyrene.
Yeah. Okay, so wool is above styrofoam. People, if you want to, they've got it figured out here from the chart. If you want to get them oppositely charged, the styrofoam cup rubbed with the wool theoretically should make a negatively charged cup. The styrofoam cup rubbed with the saran wrap should produce a positive cup. And we have them attracting right up here in front, so it does work.
Why did it repel? The first time it repelled.
Saran wrap? Yeah.
It really, that is
Okay.
Give up electrons.
Okay, using the styrofoam cups on threads is a more controlled way to have students investigate the nature of electrostatic charges. Advantages being at elementary level, you're not going to have the mess. Also, if you want to do some qualitative studies in some more detail at the middle school or high school level, by using the styrofoam cups and this list of electronegativities, they can, decide whether they're going to have attractive or repulsive forces, make predictions, and then test those predictions in a scientific way. Okay, I hope that you enjoyed that segment of this in-service. But basically, what we want you to remember from this portion is the following. That when you rub two dissimilar objects together, be they cloth and plastic or fur, whatever the two objects happen to be, that the separation of charge occurs because it's the electrons that are moving. The electrons, if I rub this marker, for example, with this cloth, it may be that the electrons move from the cloth onto the pin. If that was to occur, the cloth would become positively charged because it has lost electrons. The pin would become negatively charged because it has an excessive number of electrons. All matter is composed of negative and positive charges. If they're equal, the object is said to be electrically neutral. But if it gets an excess of electrons, it's said to be negatively charged. And if it has a deficiency of electrons, it's said to be positively charged. And then once they become charged, they will exert a force on each other. If the charges are opposite, they will attract. If the charges are the same, if they're both positive or if they're both negative, it'll be a repulsive force. In the next segment, we're going to show you how to use magic tape to separate charges. Well, welcome to part 2 of our workshop on teaching about electrostatics. This portion of the workshop is entitled Magic Tapes. We're going to be using magic tapes to separate charges, much as we did in the first portion, only we're going to focus in this part with using the magic tape. So, now the tapes truly are not magic, but that's just a trade name, so we're going to use a trade name. This is the second part of part 3 of the AAPT manual that I spoke about before, written by Robert Morris. And this is a manual that should be accompanying this workshop as you watch this videotape. For this one, you need to have the small of the variety of materials that you had for part 1, but you also need to have the Scotch magic tape. So I'm going to walk over here to the lab table now and show you what we'd like you to be trying. Basically, you will put down the magic tape. You put an initial strip of magic tape down on the tabletop. And the surface really isn't too important. It should be clean. But we want about a 30-centimeter piece of tape that we're just going to stick down on a surface like this. And this will be the base tape right there. That's going to be right on the tabletop. And then we're going to take another piece, about half that long, or about 15 centimeters long. And at one end, we're going to fold over about 1 centimeter to make a little tab that's not going to be sticky. So we can grab a hold of that and not get it sticking to our fingers, okay? And then we're going to press this down on the first piece of tape and rub this with your finger back and forth. And then what we're going to do is ask you to pull this piece of tape up with your tab. You've got the tab piece right over here. And you can just quickly pull that off of the other piece of tape and then test the various objects. For example, you have your pieces of paper, little bits of paper we started out with in part 1. You can cut some little pieces of little bits of paper out there to see what the effect is with that. You've got the other objects, you've got the straws, the cups, all these other things. What I'd like you to do is to pull that tape up now and see how it interacts with all these other objects and see if you can determine whether or not there's charges there. Why don't you turn the tape off now and try it?
So are we testing what on the table or what?
Yeah, but I pull it up, and I wouldn't have anything too close to it because it tends to be pretty charged. In fact, one problem you may have when you pull the tape up is it tends to flip up and it'll hook up on your wrist or your finger or your knuckle or something if you get it too close.
Pull it all the way up or just?
You just pull it all the way off. And it's
Yeah, test the one you pull up.
Should we keep resticking it? Pull it right up?
Yep.
What's that?
Should we restick it and test the different objects?
Just one time should do enough. You should be able to.
This is why you can't take
Are we still?
If you get stuff that is attracted to the sticky side, you probably have to use another piece of tape.
This is just, whoa.
Getting
Okay, you may want to try it again once you get all stuck up with all that stuff. You may want to have charge a tape and then compare it with your partner's tape. See if all the tapes are charged the same or different.
First of all, ready? Yeah, let's do this.
Get a tape to the charge.
Got this charged with contaminated.
Two tapes. This is repelling too.
Okay, one question is, we have this electronegativity series where we have two different objects rubbed together, transfer charge, right? But here you've got scotch tape and scotch tape, or magic tape and magic tape. Two same objects, right? Why should there be charges transferred?
It's two different sides.
Something to think about. What's that?
Two different sides to it.
Yeah.
Okay, you've got one side with the adhesive, the other side is the non-adhesive side. So it's really two different objects. Think about the tape as being, smooth plastic on one side and the other side having the adhesive. So you really have the adhesive to the smooth plastic.
So are you saying that if
So
you put the
there's really two different objects.
Wild man.
Well, this has got the tape in on it.
This one.
Sticking up for each other.
Wow.
Oh, okay. Post-it notes can be used in your experiments too. He found out back here that the sticky part of the Post-it notes, repels the adhesive side, and the paper side of the Post-it notes attracts it. For this section of the magic tape portion of the in-service, we'd like you to take one piece of tape and charge it just as we did in the first portion by putting it on your base tape and rubbing it with your finger. Oops. Pulling it off with the tab. But this time we want you to just hook it on the edge of the table or an overhead support such as I have here, and then charge another piece of tape identically to the first. Make a little tab on the end, put it on your base tape, and rub it in, and pull it off of there. And now I would like you to try bringing these two pieces of tape close together, because since we charged them exactly the same way, you would guess that they were charged identically. And you all know what happens with like charges, right? Well, let's find out if they repel. Stop the tape and try it. The question is asked, sticky side facing each other. I would suggest that you have the non-sticky sides facing each other, because if they happen to attract, you're not going to be able to pull them back apart again.
You stuck it to the bottom of the table.
Oh, they're repelling.
Does that surprise you? She says they're repelling. Well, we did the same thing to both pieces of tape, so they will be repelling. Oh, that's excellent back there. We have a charge indicator back there. I don't know, can you pick that up with the camera?
Wait a minute, where's that spoon?
Okay, I hope you discovered that the two tapes repel each other. We had two pieces of tape that we charged exactly the same way, and therefore we could assume that they had the same charge. Now, we don't know if the charge was negative or if the charge was positive, but we would assume that they were the same. When you brought the piece of tape up to the suspended piece of tape, you should have observed a force of repulsion there. Now, I was wondering, is there any way that we could take two pieces of tape and charge one way and the other one the opposite way? Well, it turns out there is. Let me show you how to do that. We're going to take, just like before, a 15-centimeter piece of tape. We're going to fold over a centimeter at the end for a little tab. We're going to put it on here, and we're going to rub it down. But we're going to mark this tape with a B. This is going to be the bottom piece of tape. Okay, so we're going to put a B right on here for the bottom piece of tape. Then I'm going to take another piece of tape. Now this is actually what you might consider the third piece of tape, because I have the base piece of tape on the tabletop. I have the bottom tape on top of that base tape. And now I'm going to put this piece of tape right on top of the other one, okay? And I'm going to call this top tape the top tape with a T. I'm going to put a T right on there so I can tell these apart. Now, here comes the important part. What I'm going to do now is to remove the bottom tape with the top tape stuck to it, okay? So actually I'm lifting up on one tab, but I'm going to bring with that one tab two pieces of tape as I lift these up. Now here we go. Okay, now I have both the bottom and the top tape in my hands right here. And now what I'm going to do is to get them unstuck from my fingers, and quickly pull these apart. Now, one problem you'll have is a tendency for these tapes to stick to your hands because they do become charged. But the question is this: if I rip these apart quickly, will they have an opposite charge? Stop the tape and try it yourself. Now, this is very nice because even if the weather is not too cooperative, the tapes are pretty easy to control the charge. So now you have a way to charge tapes the same and charge them oppositely, right? To demonstrate some of these properties about electrostatics. And again, the materials for this activity are very cheap and inexpensive. You know, one roll of tape is good enough for your whole classroom. And they can actually experience this attractive and repulsive force very simply with this.
Why is it important to pull the bottom tape off first and then the top?
Because otherwise it won't work.
Good science answer.
Because if you pull, I think, now you have to try this to find out. I think if you pull the top tape off first, then you pull the bottom tape off second, you'll end up with two tapes charged the same way. And they'll repel.
This one's going to be opposite on the table from the one I lift up on. This is going to have the opposite charge on this one.
Or should you say this?
It should be. Oh, I didn't do it yet.
It gets to be much more complicated. I mean, I don't want, you know, you give this impression that when you rub things, you transfer electrons, and it's real simple. It's really not that simple. It's a very, very complex process, and it really gets down into the way the molecules are bonding together and the state of the electrons in the outer orbitals of those molecules, or the atoms that are in those molecules. So it's not a real simplistic, you know, thing. It's a lot more complicated than what we tend to talk about. With younger kids, it's really hard to get into some of those difficult things. One thing is that electrostatics is predictable, but not always absolutely. A number of you have already experienced a behavior one way when you do it, and then you repeat it again and you get the opposite kind of behavior. That can happen with electrostatics. Okay? Yes?
I've got one set that doesn't work as advertised.
You got what?
I've got a set that never works.
Okay.
And I'm not sure if it's because there's tape to tape on one of them. from my
Your,
holder.
what is it, your magic tapes are not
Yeah.
being magical, is that it?
Right. I'm not sure what the,
And where did, what happened? I mean, this is where you,
they're always repel instead of,
oh, okay, when you pull the, okay. When you pull the two up together, they repel?
yeah.
Okay, let's check that out. Let's see.
Right.
You got one down. Now, you got one problem there because that's longer than your base tape. So let's
You're saying that the. they
I'm
have to
saying
be
let's
a-
get some new tape.
Okay.
Yeah, let's get some new
Well,
tape.
it works with different tape. It just works under, it doesn't work with this. We've tested it over here with that.
Oh, with those tapes it doesn't work?
Right.
Well, now the one was longer than your base tape too. You're just rubbing one end of it. I'm thinking that you could have some residual charge in the rest of it.
Okay.
I don't know. Okay, I hope you learned how useful magic tape is in electrostatics. Very simple to charge it, very inexpensive. You can hand out enough for your whole classroom to work with hands-on. And with the techniques I've shown you, you now know how to charge the tapes so they're charged the same, or you also now can charge the tapes so they're oppositely charged. If they're charged the same, you can show the students the force of repulsion. If they're charged oppositely, you can show them the force of attraction. Many, many open-ended experiments are possible by using these magic tapes in conjunction with the other collection of electrostatic materials we have here. In the next segment, called Electroscopes, we're going to show you how to build some very simple, inexpensive devices that it makes it easier to demonstrate this force of repulsion and attraction in electrostatics. Hello and welcome to the third portion of our workshop entitled Teaching About Electrostatics. This portion of the workshop is entitled Electroscopes. Electroscopes are devices that are made to detect electric charge. It actually operates by having a combination of conductors and non-conductors arranged in such a way that the portions of the electroscope will become similarly charged, and then those portions will repel each other and there'll be some type of motion. Here in front of me I have a commercially produced electroscope, and these things run, I don't know, $10, $12, maybe even $40 in some cases. And I'm going to show you in this portion of the workshop how to make some for yourself with simple, inexpensive materials that even your students can make. But let me just show you how this operates. I'm going to take my rabbit fur and golf tube here to get a little bit of charge on here. And you'll notice the straw, which is in the center, already reacting to the charge that I'm developing here. And you can see what's happening. The straw is repelled because of the charge that's on there. Now, since the golf tube is a non-conductor, the charge is not really conducted directly into the electroscope that easily. So I kind of have to wipe the charge off onto the electroscope. But there you can see an electroscope which is charged. The greater the angle that the straw is at, the greater the charge in the electroscope. If you look over at our workbench or our lab table over here, you can see what you're going to need for this portion of the workshop. We actually have an arrangement of materials there. First of all, you're going to need some aluminum foil. You're going to need a coffee cup, some thread, a plastic straw such as you get at McDonald's. You know, next time you go, just take 2 or 3 extra ones for your workshop. A glue stick and some scissors. Okay, the first step in making your own electroscope is to make what I call a silver straw. This will not only be used in electroscopes, but it will be used in a number of the activities that we're going to be working on with this particular workshop. So we want you to start out with a small piece of aluminum foil. We're going to use for this portion of the electroscope only the following materials. We need to have your straw, the glue stick, and some aluminum foil. So I'm going to take out a small strip of aluminum foil. From our roll here. And flatten this on the table. Get a pretty smooth layer of aluminum foil. This is about the same width as my straw. And I only need to coat like 1 coating around here. So what I'm going to do is to kind of estimate how much I'm going to need to roll my straw around here. And that's just a very small portion. So then I can take and cut the aluminum foil into an even narrower strip here. Like so. And again, we're going to try to flatten this out as level as we can. And you may want to put some wax paper on the surface below this because, especially if you have students do this, it can get a little bit messy. Take our glue stick out, and now we're just going to coat the dull side of the aluminum foil with glue. Simple as this. Okay, now take our straw on one side, seal the edge of the aluminum foil to the straw, and then just simply roll. And that is all there is to it. You now have your own silver straw, which will be useful for a number of our different activities. What we're going to do is to trim off our end here. And then if we cut this into short segments, we have small units that act as a charge indicating device. We have a conductor, which is the aluminum foil, coating this device, and this acts as a very inexpensive and very effective charge detecting device. See here I've taken and cut 3 little segments off the glue. You really should wait until the glue dries, but this will work for our purposes. So there we have some of our little charge indicating devices referred to as pith balls, P-I-T-H, pith ball, because what they used to use in electrostatics were the inside of trees, the soft material on the inside of a tree, and then they would have to coat that with aluminum foil. This is just a lot easier and simpler to do. Okay, now that you've got your piece of silver straw manufactured, we're actually going to build the first and simplest of the electroscopes, which are pictured here in the manual that I've spoken so many times about. This is the pith ball electroscope. We have our cup placed upside down. We have a piece of masking tape to attach our straw to the side of the cup. Like so. And then we just bend the straw. This is the ones that have those little flexible places on them. Very handy for this. So you just bend it over at right angles. And now we take a short piece of thread. And with our little silver cylinder, a little segment of the straw, simply run this through the middle. Tie this into a knot. Like so. It's a good idea to trim off the excess thread that's hanging down here, because that always tends to get in the way. And then what you can do is just measure this, see about how long you want this to be. And I just use a small piece of masking tape. You can tie it on the top of there if you want. But just take a little teeny piece of masking tape, suspend this right from up here, put your masking tape over the thread, and there you have your little simple electroscope. And how's it work? Well, again, if you take objects that you charge up, and you can experiment with this, I'd like you to stop the tape in just a few seconds and get your collection of electrostatic materials together and bring these up there and see what happens when you charge your little electroscope. So we'll let you turn off the tape now and play around with this for a little while, and then come back and we'll continue with the workshop. The advantage to this is that you have a conductor. The little bit of thread, a little bit of straw with the aluminum on it is a conductor. And what happens when you work with conductors is that the charge will be transferred like immediately. It doesn't take time. And so if you touch it with a non-conductor, you can wipe the charge onto it, and it just reacts a little more immediately than the non-conductors do. That's working excellent back there. That's great. No, if it's repelling, you know that you don't have an induced charge. Now, what you might try, you have this repelling right now, right? Okay, touch it with your finger to discharge it. Okay, and now touch it with, go back with the spoon again. And what happened? It happened really quick. Yeah, so if you start with an uncharged electroscope, in other words, touch the little silver straw with your finger, and then bring your charged object up. Watch very carefully because it happens rapidly. It'll first be attracted because that's induction, okay? And then when the metal touches a charged object, it takes away the same charge that is on the object, and then it repels, okay? So it's a very good way to show that process of induction we talked about earlier in the in-service. Now, if you want to have some fun with this, try this. Bring up your charged object on the opposite side of the object, put your finger so that the little silver straw can bend up and hit the tip of your finger.
Ping pong ball.
Yeah, I love that.
You see that work just sort of.
Holy mackerel.
Now, conceptually, if you get that thing vibrating back and forth, you understand what's happening.
Switching off transfer.
Yeah, the little silver straw acts as a little, like a ferry boat for charge, okay? It takes a charge from the object to your finger. You are a conductor at the voltages we're working with for electrostatics, so your body is a conductor, and it takes that charge to ground, and then it is an uncharged silver straw, which is then attracted because of induction back to the charged object, picks up a charge, is repelled to your finger takes the charge away, and it just repeats over and over and over again. Okay, this next electroscope takes a little bit more patience than the last one did. What you're going to need for this are two of the bits of silver straw that I have here on the tabletop, and a very narrow piece of, I have some aluminum foil here. You could use tinsel from Christmas trees for this. And what you need to do is to use your glue stick and attach these straw bits to the end of this strip of foil. And that's what takes the patience. So what I've done is I've already built this. I put this together already. And it looks like this when it's completed. What you have here is a glass or actually a jar, whatever you have handy to use. And then I've taken the two bits of straw that are on the foil and suspended them from another aluminum foil coated straw. And so since the foil is a conductor and the suspending foil is a conductor, if I put some charge on here, the charge will be carried down to the two bits of straw and they should repel each other. So let's take a look and see how that works. Now, of course, we want you to build your own and try this out, and you might even have some other design options. As you get more and more used to some of these devices, you might come up with your own ways to build these. But I think there you can see the mutual repulsion of the two bits of straw. I think that shows up on our monitors here. So that's another simple form of electroscope that you can build. Now the next electroscope, and I'd like you to, when I get through showing you how to do this, stop the tape and make one of these for yourself, is, in contrast to that last one, not very difficult at all. This requires a soda can and a coffee cup, and we're simply going to tape the soda can to the top of the coffee cup like this. We're going to take a small piece of aluminum foil that I have here, fold it in half, and then just set that right on the little ring, the tab ring right here, and pull this down like that. Now you may want to put a little piece of masking tape on the edge just to hold that down so it doesn't fly off of there. And we can trim the rest of this masking tape off here because we really don't need that there. And now, let's see how this works. Better yet, you should actually stop the tape now, build one of these yourself, and check it out for yourself to see how well this indicates the presence of electrostatic charge.
And then you put the foil on the end. You put it through and then you still
I've made this before too.
What is the purpose of building these devices? An electroscope is a device that is used to detect electric charge. In other words, it's a little more sophisticated than seeing if you can pick up little bits of paper. It has the advantage of being a conductor, and so it's a little more immediate. It'll respond a little more immediately to electric charge than little bits of paper. But it's simply a device to determine or to show that there is electric charge present. Well, charge it. You got it built? Charge it. Just, yeah, get your, like, what works good, the spoon and the cloth or whatever? What did you use to charge for this thing here when you charged it? Okay, the soda can, again, is a conductor. The tinsel, aluminum foil or tinsel you put on there is also a conductor. That tinsel is like plastic, a non-conductor, but coated with a thin metallic coating, which is a conductor. And the can tends to act as a little storage, okay? So it may not be as sensitive as the other electroscopes, but it has the advantage of kind of storing the charge. They have multiple, wow, they have multiple fibers. No, you're charging one way and one the other way, so they're attracting?
Actually, no, we must be charging them the same way. This is what
They're repelling now?
Yeah.
I don't know about those scissors you guys got over here. That's strange. It's supposed to, when you touch the scissors or something, it should take the charge away, but...
Maybe magnetic scissors.
She's a metal to...
There's a lot of products you can buy, food products you can buy, that are wrapped in this metallically coated plastic material. That is a real good resource for this. This tinsel, I'm fearful, is a little bit too fine to just act as like two strands to separate. So you have to go with aluminum foil. Aluminum foil is a little bit on the stiff side. So that metallic coated foil might be excellent. There's also some candy bars, gum, other things that have that wrap that you can find. So if you just keep your eyes open, you'll see all kinds of resources that you can use in your classroom like that. The electroscope is a very good example of how we use a combination of conducting materials and non-conducting materials. With our commercially available electroscope right here, you can see that the inside of this has a metal stem that comes down this region right here. This is connected with a bolt to this metal plate that's on the top. The material, this white material, see right here, is a non-conducting plastic, so that that is not going to be in connection with this surrounding can part right here. Now, when the top part becomes charged, the charge can be transmitted through the conducting material right down into the stem and onto the straw through the little pin that's on here. And when they both become charged the same way, the straw is then repelled from the other stem, and it moves to the side like this, and you can get a reading on it, okay? Of course, it doesn't work now because I've got it laid down here so you can see how this operates. But let's take a look at our other electroscopes and see what parts of those are conducting and non-conducting materials. If we step over here to the lab table, we have our 3 electroscopes over here. And on this first simple form right here, we have the straw and the cup, of course, are non-conducting, and our silver straw fragment right here is the only conducting portion. So we bring a charged object up to this. This is just repelled. Now, this is a little different design. Our other 2 are set up so that they have 2 conductors which are close together. In the case of this simple form right here, we have these 2 little pieces of silver straw suspended with the conducting medium, and when they become charged, and they will separate and repel from each other. With our soda can version right here, with our 2 little aluminum vanes sticking down, when they become similarly charged, they will likewise repel and move apart from each other, and thus show the presence of our electric charge.